In this lecture we're going to go through the binomial distribution. In particular we're going to talk about hypothesis formulation and testing. So a setup is that we have a triangle test where each judge is presented with 3 glasses, and in 2 of the glasses there is the similar content and in one of them is deviating, and then the judge is asked to be able to differentiate, so figure out which of the 3 glasses is the odd, the different glass. So in this case you either answer correctly or answer wrongly. So the learning objectives is to be able to formulate a null and alternative hypothesis based on design and data, and then to test this hypothesis. So what is binary data? So here is an example of binary data where we see 18 different letters, and each of them is one trial, so 0, 0, 0, and then there are some ones. And you can think of it as either or data. There is only 2 possibilities at each trial, so either it's 0 or it's 1. It can be toss of a coin, measurement of the height of some person, whether it's over or above or below a certain threshold, or whether an answer is correct or incorrect. Positive or negative tests, for instance. This is the same data as before, just in a different representation, where we say, well, there is in total 18 trials, and there is 6 of them which are 1, and the rest is 0. So these data are described entirely by the number of tests. How many of the tests which are 1, we call that x, the number of tests n, and then a probability of x, which we call p. In the testing, in the hypothesis testing, we use the so-called cumulative probability distribution in order to answer the questions we raise by the hypothesis. So the cumulative, a recap on that one, is that you take the probability of observing an x less than a given number, less than or equal to a given number. And that is naturally simply just summing the point probabilities of 0, 1 and up to the given number x. If you want to answer the question, what is the probability of getting a value above a certain level x, it's the same as above, where you summarize point probabilities from that level and up to n. You can turn this one around where you're saying 1 minus the probability of observing less than x, or the probability of observing less than or equal to x minus 1, and then 1 minus this one. So, hypothesis test. First we state a null hypothesis. So in this case we say, well, the hypothesis is that p, the parameter of the binomial distribution, this p, is some value q. And then we calculate the probability of the observation, or what is more extreme compared to the null hypothesis. So an example of this would be the triangle test. So I have a test here. It's a triangle test where we say, well, we have we have 40 judges, and they are presented, each of them are presented with 3 glasses, 2 of them with a similar type of product and 1 of them deviating. And the product is apple juice, and the difference between the 2 glasses, the 2 different types of glasses, is whether there is citric acid added or not. From this trial, a total of 20 judges answer the question correctly, whereas the other 20, they answer it wrongly. So let's just see how this is done. So first of all, we formulate that x is the number of correct answers and that x, furthermore, is binomial distributed with n and the parameter p. In this case, n is equal to 40. Then we say, well, the null hypothesis in this case is that the judges, they guess. So we formulate that as P equal to, and if you are presented with 3 classes and should distinguish the odd sample, then if you do not have any clue about which one it is, you will by chance hit the right answer 1/3 of the times. So this is the null hypothesis probability. We sometimes put a 0 here in order to reflect that this is the null hypothesis. The null hypothesis is 1/3 for a triangularity test, but it can be any other types of probability that's simply based on the setup of the data and the trial. The alternative in this case is, well, if we say, well, they are not guessing, then we would say, well, in that case, more than 1/3 is able to distinguish the samples. So we say that P is larger than 1/3. Okay, so now we observe x equal to 20, and now we wish to calculate, is there any support from the data on the notion that this hypothesis is true? So what we do is we say, well, 20, that's a little bit more than 1/3 of what we would expect if they were only guessing. If they were guessing, we would expect that around 13 to 14 of the judges would answer correctly. So 20 is a little more. But we would like to know if this little more is due to chance or whether they are actually capable of tasting differences. So we calculate the probability of observing an x which is larger than or equal to 20, given that they are all guessing. So now we assume that they are all guessing, and we calculate the probability of observing this number. So this one is equal to 1 minus the probability of x being less than 20, which is equal to 1 minus probability of x being less than or equal to 20 minus 1. So let's just go into R and see how this is done. So first I define the input. So in this case, n is equal to 40. The P0 is equal to 1/3. And now I wish to answer the question, which I have here. What is the probability of observing more than 20 samples? More than or equal to 20 samples being correctly, which is the same as this guy over here. This function is called P-binomial, and we put in 20 minus 1, that's the proportion, n, and the probability. So in this case it's 0.02. So this one equals to 0.02. So in conclusion, we would say, well, it seems rather unlikely, 2% of the times, that we would get as much as 20 correct answers out of 40 tests, given that they are not capable of tasting any differences. So from this we will say, well, the data supports the notion of them being able to distinguish, at least some of them, to distinguish the two different types of juices.